Last week we talked about beta diketones or beta diketoesters as excellent sources or excellent substrates to make enolates as a nucleophile in the Michael addition. It turns out that if one of these is a carboxylic acid, this can undergo a process called decarboxylation, in which you lose CO2 and we get an H there eventually. And this can be a very useful reaction in synthetic chemistry. And so this actually can happen under acidic or basic conditions. And so let's take a look at how that can happen. Under basic conditions, this requires a little heat, and these electrons are going to go up and form a carbon or oxygen carbon double bond, which is going to kick these electrons over and these electrons up, which will result in an enolate plus CO2. This enolate in a second step can then get protonated to, in this case, form a ketone. And we have lost carbon dioxide in the process. This decarboxylation reaction only works because we've got this beta ketone or beta carbonyl. And so when CO2 leaves, we form this resonance stabilized carbanion or the enolate. Without this oxygen to form an enolate, the leaving group would leave too much of a negative charge on carbon. We're not going to form just any carbanion. And so the beta dicarbonyl is necessary. This will actually happen under acidic conditions too, and if it's under acidic conditions, they can be a little milder. You don't necessarily need heat for this. And so the first thing that's going to happen is we're going to rotate around that carbon-carbon bond to get the OH group at the top. I'm going to draw out my hydrogen-oxygen bond there too. So after you've rotated into this conformation, in a concerted mechanism, this oxygen is going to deprotonate that, which is going to kick these electrons down and kick that up and those electrons up. And that will result in an enol plus CO2. Enols readily tautomerize under acidic or basic conditions. And so in a series of steps, this tautomerizes to give the ketone, in this case, plus CO2 again. So if you have a beta carbonyl to a carboxylic acid, so we've got a alpha carbon, the beta carbon, so if there's a carbonyl on the beta carbon of a carboxylic acid, it can decarboxylate and lose CO2 in basic or acidic conditions. We can use this decarboxylation process to make certain compounds. And so one option is to make a carboxylic acid using the malonic ester synthesis. Malonic ester synthesis gets its name because this is malonic acid. And if you make an ester out of that acid here, you can use that in the malonic ester synthesis to make a carboxylic acid. And so in step 1, we've got sodium hydroxide or sodium ethoxide. That's just going to deprotonate the alpha proton to give the enolate. And I didn't complete my arrows up top, so we'll go back and do that. This arrow is really going to that bond. And then in a second step, we add the alkyl bromide. And so that does an SN2 attack on the alkyl bromide, like so. To give this. And then in a third step, we add water and HCl and some heat. The heat is required to cleave the esters. And so in the first step, we are going to hydrolyze both esters. To get that. And then in the second step, we're going to do the decarboxylation, and we'll go through that mechanism again. We're under acidic conditions, and so the first thing we need to do is rotate about that carbon-carbon bond. And didn't show the rotation there. And then we give away some electrons there, kick those electrons down. That folds over, which kicks that up. So that loses carbon dioxide. And forms this compound here, which is going to tautomerize to form the carboxylic acid, like so. And so the carboxylic acid portion of this molecule plus the alpha carbon came from the malonic ester we started with. And the other carbons came from the alkyl halide here. The malonic ester synthesis can also be used to make a carboxylic acid that has 2 alpha substitutions. And so in this first step, we deprotonate to form an enolate and attack the alkyl halide. And so the first intermediate is going to be that. And then in steps 1 and 2, in the next series of reactions here, we're going to alkylate again. So we had the benzyl group attached, and now we're going to add a propyl group. So that's 1, 2, 3 carbons. And then in the final step, we're going to decarboxylate, and that's essentially going to be losing this part. And of course, these acidic conditions are going to cleave that to an OH. So we get benzyl propyl. So if we're identifying where everything came from, that came from our starting malonic ester. Specifically, it's 1/2 of this. Then the benzyl group came in the first alkylation step from the benzyl bromide. And the propyl group came from propyl bromide in the second alkylation step. The acetoacetic ester synthesis is very similar to the malonic ester synthesis, except that we're going to use it to form methyl ketones instead of carboxylic acids. And in this case, again, it gets its name from the starting material you use. This is an acetoacetic ester. And in the first step, again, we're going to deprotonate the alpha carbon to form an enolate, and actually it's going to preferentially form the enolate on the ketone side because ketones are better at stabilizing enolates than esters. And just like before, the next step is going to be attacking the alkyl halide. That's propyl bromide, and so I need to make sure I add 3 carbons. That's 1, 2, 3 carbons. And in the last step, we're going to first hydrolyze the ester. To form a carboxylic acid, which under these acidic conditions will decarboxylate. To form a methyl ketone. So methyl ketone here. I have a methyl group hanging off of one side of the ketone, and that's coming from my starting material, or the acetoacetic ester. And this propyl group, again, is coming from the alkyl halide that I started with. Just like the malonic ester synthesis, the acetoacetic ester synthesis can be used to make 2 substitutions at the alpha carbon of a methyl ketone. And so in steps 1 and 2 here, we're going to add a propyl group to the alpha carbon. So a propyl group is 1, 2, 3 carbons. And then in steps 3 and 4, we're just going to repeat the process again. And so that's going to add another propyl group to the alpha carbon. One, two, three, and then 1, 2, 3. So we've got dipropyls now. And in the 5th step, we will cleave the ester and then decarboxylate to form 1, 2, 3, 1, 2. This ketone as the final product. Again, if we're identifying where carbons came from, this portion came from the acetoacetic ester. One of these propyl groups came from the first alkylation, and one of these propyl groups came from the second alkylation. That's going to wrap up today's video on decarboxylation and its use in organic synthesis.